So it's an honor to be here at the DAC to give the keynote. DAC is the community I've been associated with for more than 30 years throughout my entire career. So like many of you, my first DAC paper was written when I was a graduate student back in 1988. If you look at the title at that time, the hot topics or physical design, in fact, a two-layer channel routing. The technology at that time, we were using Intel 386, designed in 1985, about a little bit over 250,000 transistors and in 1.5 micron technologies. And a year later, after my keynote, after my first paper, that Intel rolled out the first processor over 1 million transistors and in 1 micron technology. Fast forward, and that's the technology we have today. For example, we have people from NVIDIA sponsoring some of the activities. The B200 has over 200 billion transistors in 4 nanometer technology. And I'm sure you're using solid-state memories and the Micron. This is even 2 or 3 years ago has 5.3 trillion transistors in 3D stacking technology with over 200 some layers. I think the latest has over 500 layers. So you can see I have the opportunity and the pleasure to see the Moore's Law in action. And the integrated circuits, by far, is among the most complex man-made objects in the world. If you ask ChatGPT or Gemini, says, what are other complex man-made objects? And they will tell you that the space station and also the Hadron Colliders. Those takes 15, 20 years to design. And however, integrated circuits today, even with hundreds of billions of transistors, are designed in 12 to 18 months. Right? So this community has created a very elaborative and a very I would say successful, impactful design flows. You start from system specification, and you have behavior description like a C, C++, or System C. You synthesize it to RTL, VHDL, Verilog, and then you get it down to general Boolean equations. Remember, all the digital circuits only knows Boolean logic. And these are the kernel maps we used to optimize when we were in undergrad schools. And from there, you generate a netlist. This is specialized to a particular fab technology, for example, TSMC or Samsung, so on and so forth. And then you have the choice to go to physical design, either create a bitstream on the FPGA or the GDS on the ASIC. This whole flow has been refined over the last 30, 40 years, and that's how it enables us to design these complex integrated circuits in 12, 18 months. The integrated circuits are no doubt powered the entire digital transformation of the society in the last 30, 40 years, and including the AI, the ML revolution in the last decade. So if you look at these two Turing Award winners, and Jeff Hinton and Yang LeCun, in fact, Jeff also won the Nobel Prize, right, in physics. So they actually was very explicit giving credits to this community because this is actually a lot created by the computing technologies. When I was taking classes on AI technologies, we have two-layer neural networks. You cannot go very far. These days, we can go hundreds of layers with billions, maybe even trillions parameters. The AI computation today, actually most of them are not done on CPUs, are done on specialized hardwares called the accelerators. So this is due to the rise of customized computing. So because even back in the late 1980s or early 1990s, you can see that if you just do simple scaling, the thermal density will be very, very high. So that's why we make the right-hand turn to go with parallelization. You keep the frequency, but you add more and more cores. In 2008, we wrote a proposal to the National Science Foundation. That's what 17 years ago we said the future is actually customization. You want to adapt the architecture to the workload, not one size fits all, but you want to be able to handle different workload with different kind of specialization. We wrote a proposal to the National Science Foundation, Expeditions in Computing program at that time was considered to be one of the largest programs, $10 million over 5 years. You can see that in the proposal we said we want to go beyond parallelization to look for domain-specific customization. So that was our view, and the application domain we chose was medical imaging because we had to choose something with impact to the sort of quality of life. But very soon it was shown by both industry and academia that the machine learning is a perfect domain to customize. Over the last 2 decades, my lab, CDSC, Center for Domain-Specific Computing, has done a lot of these specialized customers or customized customers, accelerators that are in medical imaging, that the applications, genomic sequencing, and the machine learning, that sequence-based, recurrence-based models, CNNs, and also big data, that compression, decompression, very large-scale sorting. And even something that you will think are very difficult to parallelize, like satisfiability problems, which is another significant workload, right, in the community, and like stencil computations. A lot of them are implemented on FPGAs as the prototype, but we take some of them to ASICs, like the SAT solver is actually being fabricated through TSMC as we speak. This is in collaboration with many of the domain experts. However, eventually the chip was done by my PhD students. So natural question is that, do we have to get involved? Can we just enable them to design chips by themselves, right? So the answer is actually not so trivial, that how many people can do chip designs? Does people know the answer? So not too many. That we look it up from US Bureau of Labor Statistics. We have about 2 million people. They claim they are software developers. I assume they make a living by software programs. That's less than 100,000. They are hardware designers. I cannot find a category called IC designers, so I just lump everything. I assume they, including PCB board, maybe putting the chassis together to form a PC or workstation. Everything's included. So the ratio is more than 20, right? That the fraction people who can design chips. You says, well, maybe the future is better that we can train more students to do that, but that's not the case. I will show you the application pool to UCLA. I'm in the computer science. Helen mentioned I'm both in the CS and EE, so I see the numbers. The bar on the left, this is a statistic for the last 5 years. Our application to CS department, we have 2 majors, computer science and CS and E. On the right-hand side, electrical engineering. The ratio is not 20 to 1, but it's quite, the gap is quite large. Some years ago, maybe 2 or 3 years ago, EE introduced CE major, computer engineering, share with CS. So I didn't count that. The number is small, and also it's not clear how to split between CS and E. But my point is that most of the people are interested, young people are interested in doing softwares. So a very natural question is that, can we enable them to design chips, right? So that's the focus of my lab in the last 20 years or 15 years. After some work that 3 years ago, I wrote an article that in CACM, this is a communication with CMS, as a democratized domain-specific computing. Really, what you want to democratize is the chip design to enable domain-specific computing. Now, our goal is very clear. We want to empower interested software programmers to do chip designs, to create domain-specific accelerator for their applications. What do you mean by, what I mean by interested? Those software programmers, they care about performance. There are also just software programmers write the HTTP code for a website. They probably never were going to optimize their code. But for ones that actually do simulation, they do machine learning, and they really want to actually rewrite the code to some extent for a better CPU and the GPU performance. Those are the ones we want to enable them to create customized accelerators. What's the reason? I think they will have a motivation, because when I was a graduate student, I was very fortunate. You write a program, you put it aside, don't do anything, it gets faster every 2 years, just because the Moore's law and also linear scaling. So now that's coming to an end. If they want to get better performance, they have to do something. And there's no more free lunch from automatic performance scaling. So I would say we're not alone arguing that the EDA for software programmers. And Professor Mark Horowitz was giving a keynote at the DAC exactly 2 years ago. And his title is The Life Post Moore's Law, The New Frontier for CAD. So what's the new frontier? Then he has a slides asking who are the customers and what's the motivation, why we're doing it now. Guess what? The answer are the application designers. Yes, the software people. So we actually share the same view. Remember that a few years ago that CACM article was arguing exactly the same. So I want to report to you some of the results we have, the approaches we're making to this extent. How do we enable software programmers to do chip designs? So first, I think it's important to start with the language they are using. Don't create a new language. And they are very comfortable with their languages. They are using C, C++, Python, PyTorch, and all those. But leverage high-level synthesis to bring it down. The biggest gap, by the way, between hardware specification and the software programmer is that the hardware specification is cycle accurate versus the software programmers is behavior level, right? And then we want to do automated code transformation and down to RTL. How do we do that? With deep learning, with polyhedral optimization, transformation, and a number of other techniques. And I think there's a great opportunity to have a agentic approach to orchestrate all these different optimization algorithms together. And Mark also argued an app store approach, which I think is very interesting and also promising, but you need to go back to replay his keynote on that part. I will not repeat. So the first step is high-level synthesis, and it's a topic in this community for over 20 years, maybe 30 years. And I'm glad to say we played a key role in making that widely adopted, as Helen mentioned in the introduction. So back in 2003, we were the first one decided to use LLVM compiler infrastructure to do hardware synthesis. Remember, that's exactly the compiler infrastructure you are using for your CPU code compilation, right? So, so that makes it very robust. We can pass any C code, and then we model the platform you're going to design, whether it's FPGA or ASIC, and then we support the full floating point operations. And we have a very efficient bit level that operation at that time was for medical imaging and other things, but today you can see it's so important for deep learning inferencing, right? So if you go to LLVM, that the AP Inc., that whole class of applications was due to our contribution back 20 years ago to the open source community. And the scheduling with difference constraint and automatic memory partition. So a lot of good algorithms get incorporated. So the key is to get qualitative result can match or exceed manual RTL designs. Helen mentioned the commercialization effort. We have a company called AutoESL, eventually acquired by Xilinx, now AMD. Before the acquisition by a large company, they do careful due diligence. So they had not only their internal team, they also hire an external company, I remember was a Berkeley Design Automation, had a whole bunch of benchmarks from wireless communication to DSP applications. So the result indeed shows that you can match the manual designs. So after the acquisition, as is now, you can release this to the public. So we had invited a paper, keynote paper in IEEE transaction on CAD back 2011. So you're welcome to see the detailed result. So the good news is that with high-level synthesis, you can take fairly simple and actually general C code, and press a button, you can get a chip on the right-hand side. Now, for example, this benchmarks is even not any of the hardware application coming from Polybench. That's actually the benchmark intended for the compiler community. So he says that's actually very good. Then that's maybe the end of the story. But there's one catch. If you don't do anything, the performance you get out of that running on an FPGA is actually 13x slower than running on the CPU. They say, oh, that's not what I want. I want to accelerate, not to de-accelerate. But actually, some of you have the similar experience when you're excited to take a sequential program to a multi-core environment. You don't see speed up, you see some slowdown in many cases. The key is that you have to give the hints to the compilers. And in our case, you have to give hints about the microarchitecture design. So you can see that the same program, I added 3 pragmas. These actually basically the compiler hints. The first loop, I want to do pipeline and how to flatten the inner loops. The second loop, I want to do parallelization with a parallelization factor of 15. And then the inner loop, I also want to parallelize. And in fact, I identify that's a reduction variable. That's a factor of 12. And by the way, these pragmas are slightly different from standard Vivado pragma because it's coming from another compiler called the Merlin compiler. It's another spin-off from UCLA, get acquired by AMD. It's totally open source. You are welcome to use that. So they only have 3 pragmas, the parallel pipeline, and the other one's tiling, not needed for this example. You said, okay, if you only have 3 pragmas, maybe it's not too bad. Let me just try to enumerate, right? So you have these a few loops, and these are all the possible places you can insert pragmas. And the pragma may have values, right? Parallel by a factor of 8, by a factor of 16. However, if you do it this way, actually there's a combinatorial explosion because all the combinations that multiply, not add, so you end up with over 3 million configurations. So how do we do it in a more intelligent way? So the first approach we take, I will not even say this is AI, it's almost like an expert system. Very simple, bottleneck-driven heuristic. So if I ask you to optimize the program I showed to you, what would you do? I don't know about you. For me, is that if this is the program, I would do nothing. I say, these are all the pragmas. Let me just run it. I get a report. I see the analysis. The report from Merlin compiler is very good. It will show you the breakdown of the cycle count for every loop. You say, if the J loop is the bottleneck over 90% of the cycles, I'm going to do parallel pipeline on this loop. And then you iterate. You come back to run it again, right? So iterate a number of times, and then you get a solution. You cannot improve any further. To some extent, this is like a deepest descent of that. And the result actually was quite well, doing quite well. We tried it, for example, Xilinx released a whole bunch of libraries for different applications. One of them is on vision. There's 50-some applications with pragmas. We take them out, then this system can actually discover almost all of them. So that's why the paper actually got today's Best Paper Award 3 years ago. But there was one problem. The problem is that every time you have to run high-level synthesis to get the result, that takes 10 to 30 minutes to run, right? If you do it, that in a day you can explore about about a couple of hundred examples. So, but remember I told you there are millions of configurations. So now we want to ask, we get greedy, says, can we predict performance, not in seconds, in milliseconds, so that I can explore millions of configurations, right? And how can we do that? This is where we hope deep learning can help. This is inspired by the AlphaGo, right? You can see the chessboard, black and the white pieces, you make a prediction. You don't have to play the chess all the way to the end. So that's what we want to do. So if you want to use deep learning, the first question saying, okay, where do you get examples? And everyone is very careful about their RTL designs. But remember, we had that bottleneck-driven approach we call the AutoESL. That's actually wonderful to create training examples because we started with a naive, simple examples. We keep adding pragmas on the way. Of course, we care at the very end in AutoDSC, but every intermediate steps can be a training example because all we need to do is to predict the performance, not necessarily the best performance, but every configurations. Just to avoid some bias, because this is still on a kind of a deepest descent trajectory, we also introduce random perturbations every step. So from there, we create a benchmark that is somewhere around 80,000 designs, all automatically collected. I will show you now we have even more. And the second question is that what's the representation you're going to use? It's very natural to say, hey, you have a program, I'm going to use transformers. It's a sequence model. Yes, we want to use transformers, but I want to think one step deeper because we are involved in the whole high-level synthesis development. We know inside we did not work on the sequence directly. What we did was, I told you, we take it to LLVM, right, the compiler infrastructure. You get a 3 address code, and then you get this control data flow diagram. Everything is actually performed on this control data flow diagram, CDFG, on scheduling, resource allocation, resource binding, all those things you learn in the textbook on high-level synthesis. So that's why we want to use graph as the first-class citizen, and we encode all the informations into the graph. And with the graph, it's very natural to use graph neural networks. In fact, it's a very simple extension to CNNs, many of you, probably everyone is familiar with. Instead of doing convolution with nearby pixels, I do convolution with nearby node. And in our case, we introduce also the concept of attention and the aggregation and the transformation. So, but eventually, is that every node has a feature vector, and then you keep doing message passing, and then you finish, and then you do aggregation. So eventually, the graph gets represented by a high-dimensional vector. With that high-dimensional vector, then you do decoding, to do joint decoding to predict performance and area. Area in FPGAs, you include BRAMs, lookup tables, DSPs, right, a whole bunch of resources. So that's actually the predictive model we have using. Once you have that, this GNN is normally in the order of tens of millions parameters, or maybe the most a couple of 100 millions, very fast. You can literally run it in milliseconds. So then we're going to use that to do the search, and for the final top 10, let's say top 10 designs, we'll do HL synthesis. And you also need a classifier to decide whether the design is out of bound or not. That's another story, right? I promise I will tell you a little bit about the benchmarks we created. So this paper was published in Europe 2 years ago. So we cover a range of applications, then the linear algebra, some of the ML-like application, also including the dynamic programming, others. So we have over 80,000 cases in that one. Over the years, the last 2 years, we have augmented this data set. And first, the Xilinx keep releasing new tools, and when they release new tools, we do need to do adaptations. We run a few more on the new tools, so we have this one. And also in the LED conference that starting tomorrow, my student also come up with an idea using LLM to augment using synthetic data. So now altogether, we have over 150,000 examples. All the work we are doing, and moreover, the number of kernels is in the order of hundreds. So these are all open source that you are welcome to download from UCLA website. But there's one limitation of using simple GNNs. The reason is that the GNNs, graph neural networks, originally was all introduced for social networks. That's had the widest application. Social networks are shallow. I know some of you very well, but I don't know any of you. Some of you I don't ever have met, I never met, but you can always find maybe 3 or 5 other friends can introduce it to me. That's actually called the small world problem, right? Program is different. Program is very deep. You can define a variable, and then you can use it after, let's say, 50 lines of a statement, even 100 lines of a statement. So how do you do that? And because each layer that allow you to communicate with your neighbors, if you are 50 steps away, then it's actually difficult to compute. You say, okay, why don't you just add more layers? But the problem is that if you do more layers, there's this problem well known called the over-smoothing. So that's not going to work that well. So how do you solve this problem? Well, for us, circuit designers, then we know that circuit actually has hierarchies, right? So that, for example, your loops, and you have statement in the loops, and then you form loops. Loop can be nested, that can be a loop. And then you have functions, and functions are connected. So you introduce all these nodes that for different level of hierarchy. Now you have shortcuts, because one variable can influence some other functions, then you can just jump to another function, and then the statement in another function. So you can see this, we reduce the average shortest distance after introduce the hierarchy, we can get it down to from 25 to 5, this 5x reduction. 5 is a rather magic number for us because we use 6 layers for our CNN architecture. But remember, I told you that we are definitely going to use transformer. The question is, how do we use? But we want to use graph as a first-class citizen. But, but by the way, before we go there, I want to say one more thing, is that if you look at the program on the left, that's where we want to predict the performance, right? There's 2 kinds of statements there. One is just the C programs. We can handle C++ or others, but just stay on C for the time being. The other one are called the pragmas. Pragmas tell you, I do parallel, I do pipeline. So what happened to this pragma? Pragma are actions. Then they will actually transform into another program. They will introduce array partitioning. They will unroll the loops and all of those things. So how do you model actions? The actions are really functions, right? The best way to model that is using MLPs. So that's why in these ones, so we introduce out the GNN encoder, we introduce we call the neural pragma transformer. And remember I have 3 pragmas, tile, pipeline, parallel. Each one of them can give us a new vector, and then I can concatenate them together. And then I can do merge and with another NLP. And that gives us a better encoding. So you really want to match your representation with your semantic actions. So that's the advantage. Otherwise, if you just do a simple transformer, you may lose some of those, right? But we do want to come to transformer, that how do we combine both kind of knowledge? The power of a transformer is that it has been pre-trained on a lot of other knowledges. The easiest way to get it going is that you can say, I use transformer encoding, I get something and I can also use GNN as an encoder. I just concatenate 2 of them, and maybe that's your first paper, but it's very simple paper. What you want to do is actually, we want to do better alignment, because I have hierarchy of the graph, and you have the source code. It can be segmented into tokens. So what we want to actually end up doing is so-called the multimodality learning. You always want to combine different modalities. The reason, for example, we are so capable of understanding each other because we see you in eyes, we hear what you say, we see the body actions, right? So this is what we do, is that you have all these hierarchical nodes. You also have the node represent different sections of the programs, and then we do cross-attention. The information can be passed back and forth between graphs and the sequences. And this is actually called the multimodality message passing, and eventually we use that to do decoding. So that's one way to combine the GNN with the large language models. By the way, some of them are actually still work in progress. We are thinking about the best way. The second way, actually going to be presented tomorrow on Friday, is another way to make use of the transformer, which is very powerful in doing in-context learning. So how do we teach the transformer how to understand the program? Remember, we are a big believer of encode that into graphs. So that's okay. We create a graph token, right? And then with the training data, we actually have X is a graph, which is the program, and the Y is for example, performance data. And I give you this sequence that I have so many kind of training examples, right? And then I ask you to predict the next one. All these X Y pairs, and then I give you another X, say, please predict the Y, right? So that's actually the basic idea. But for this to be more stable, you don't want it to just predict on the function you have, because that's actually can be easily the kind of overfit. You want to let it be able to predict a set of functions. And this is actually a brilliant idea out of my colleagues at the Editia at UCLA. He called basically neural TNP, the transformer neural process. So where he introduced Gaussian process as functions to guide the prediction process. But in our case, we find that it's more actually accurate. more efficient to use GNNs with random dropout and all these things, because we want to get different functions which are closer to our domains, right? So let me just contract both. In the HARP, I just told you that you will actually train the graph models with all these XY data, and then that's the pre-training. And then when you get a new design, you run the HIs a few times, then you do fine-tuning, you get a different graph encoder, and then I says, here is another paradigm, you will do the prediction Y. But in this new approach, I call that graph-aided in-context learning. So it's somewhat different. I also train that, but I don't learn from program directly. I learn from the GNN encoder, and then I encode that. I have all these sequences. I'm going to be the target, and I give you a new one, ask you to predict. Because supervised learning, I know the target, but you are going to do prediction. Sometimes you are wrong, and this is a transformer neural process, TNP, and then we'll do backpropagation to correct the transformer. So basically, the transformer will be improved over the time, so I get a new corrected prediction, hopefully. And then at the deployment time or the test time, so that's it. Then I don't need to do fine-tuning. I just collect a few designs, maybe 50 designs, running HIs. I get that sequence, then we'll say predict the next token. If I give you a new configuration, what's the token? So that's the approach you are taking. So this is the in-context learning with the graph neural network. So finally, I want to show you yet another way to combine GNN and LLM. Another student come in and says, GNN is generative AI. It's very capable of doing generalization. What about we just ask it to generate the optimal paradigms for us directly? Does that make sense, right? But can you see the difficulty? Because the paradigms are in the middle of the program. The generative AI is very good to predict at the end of the sequence. In the middle, how do you do it? Well, so that's one thing, that all these parameters you're going to predict. And by the way, we do have a faculty member, UCLA. She works on inserting things in the middle with another kind of a whole line of research for LLM. But in our case, we have a more clever way to do that. What we need to do is that we collect all these variables and placeholders, and then I will put it at the very end. Do you see that? That's actually after the program. I have a section showing these are the parameters need to be predicted, and then they will just predict the values one by one, right? So that's actually become generative because that's coming after you've seen the whole context. They come out with the value. You say, wow, that's actually clever. How do you train this? So the way we train this is that we are going to have because we have a database, remember that all the examples. So we ask LM, can you predict? It will predict something maybe not the same as the best examples we have. We trying to do backpropagation at this level is very hard because they differ only by 1 or 2 values. Paradigm on row should be, in parallel should be 15, and they use, let's say 10, right? It's a very subtle difference. However, remember we have that neural paradigm transformer, and then we use the graph representation. Again, the graph representation could be quite different because we capture the impact of the graph transformation. So with that, we use the HARP encoder, and then we can see more vividly what's the difference, and then that difference can be amplified, can be backpropagated, right? So this work is in submission, but I think it gives us a very fresh view to see how another way, different ways we can combine the GNN and the LM. I think there's an archive paper that if you're interested to take a look. Let me give you a quick overview that so AutoDSE, this is the bottleneck driven, and we have to run it for 24 hours to get some good, decent result. 24 hours, we are happy to do it if it's give us the best possible solution, but not always the case. HARP using graph encoder and then can, hierarchical graph encoder can explore a much larger universe and then give us like somewhere around 11, 12% improvement. And we can augment it with that sequence-based model, transformer-based model. The iceberg is the one actually using that augmented graph encoding with in-context learning, so that gets further improvement. This lift is the one I talked about at the very end, using pragma prediction directly. And surprisingly, you just predict directly without worrying about the intermediate performance models, actually give us better solution, at least for this set of designs. But I'm sure there's rooms for improvement. But we want to really generalize to do more design. As we generalize, we find out that actually it's not that easy, that we have that 80,000 or 150,000, but still a relatively small universe. So if I get something really out of the domain, and the point can be very different. You can see this is the visual kind of a representation of all these graph encoders. The different designs for the same, the different configuration for the same design, they tend to be clustered together. So that's why if you get the new designs totally out of this set of training examples, you can present challenges. And you run that HLS, when you see a new design, you can run it 10, 15, 50 at the time, but it's rather limited. And you have the unique, but there's some unique opportunity. You can see two designs can be very different, but most likely they share that common substructures, right? So that's actually we want to leverage. So that's where we introduce the mixture of experts. That the experts will predict different kind of the substructures, and we integrate them together. So this one, you can see, gives us much better prediction accuracy. So how does it work? So we think the common substructures can be in different forms, can be in a node, basically it's a simple loop, or can be in a block, which is a set of loops, or can be even in subgraphs, that is graph level. And then we have gating networks to decide which expert to use for which level, at each level, right? Node level, block level, and the graph level. And then we have a second level of a hierarchical transformer, that hierarchical representation is the gating network to find out how do we combine this information knowledge together. So that's actually the way we are coming up with to handle this domain shift. We are still actively working on that we'll welcome many of you to join the effort. So with this, we can get a better domain transfer. For example, on this set of new designs, basically intentionally we let HARP and everyone else to train on a subset of designs we have in the HL sim, and then test on these unseen designs. If it's totally unseen, the HARP didn't do that well, maybe 30% away from auto DSE. However, once we add back this hierarchical transformer, we can be 8% ahead compared to that. So that's a very encouraging result. I know I said a lot about the AI ML. You say, oh, let's just do it, the ILM for chip designs, but not so fast. Oh, by the way, one last thing I want to say is that you are saying that you probably notice a lot of these designs are actually prototyped on FPGAs because the students really like FPGAs. You can get one design done in 3 months, 4 months, instead of 12 to 18 months to an ASIC design, right? But in this community, there's a lot of interest, can we do prediction for ASIC designs? So we work with Cadence, and they have a Stratus HLS tool. So we want to be able to teach them that tool to do prediction. But the data is much fewer, because ASIC design is mainly done by industry, they don't release data. But we have some common database that we're actually going to run HLS, ASIC design all the way back. So, but that's very slow. You cannot collect too much designs. So at this point, we have about 220K designs we created for ASIC. We have using 4K designs to train a model. But how do you train a model? So this is where you also need to give some thought. So we have ASIC designs, we have FPGA designs, and the same backbone model to encode because they're coming from the same high-level representation. But you want to make sure that the knowledge can be shared as much as possible. So that's why we have one part of the network is representing shared knowledge. Another knowledge is that they are specific knowledge. How do you separate shared versus specific? We do so-called adversary training. We have discriminators. We say, okay, on the shared knowledge, you should not be able to distinguish whether it's ASIC or FPGA, right? On the specific knowledge, you should be able to tell right away whether it's coming from ASIC or FPGA. So that's the adversary training. So if you can separate the both, and then you join them together, you can do the training. Because you want to leverage what you learned from FPGA design as much as possible. This, by the way, has nothing to do with FPGA prototyping. Everyone goes through that. But I'm just talking about the ML prediction. So with this capability, then we can actually train a network, leveraging, using rather fewer ASIC designs, but leveraging a lot of FPGA designs we have. Let me show you that some of these designs that we can see on the left-hand side is that in terms of the, this is a latency, the lower the better. If you don't use this FPGA knowledge, you actually worse. But when you combine FPGA with ASIC, because you have a lot more training example, you can do so-called task transfer, you'll get a better result. This is still ongoing, and we're going to get more. Hopefully, we can also get more ASIC designs. We'd like to welcome you to contribute, to contact us, what we can do together. As I said, that we are very passionate about using AI ML for the chip designs, but I want to caution that that's not the only way. And in fact, I don't recommend it to using our way. I think when human intelligence prevails, let's always use human intelligence instead of artificial intelligence. How do you define that, where we understand? Let me show you some examples. If we understand the optimal architecture, the solution space, all of those, we definitely want to make use of that knowledge. One good example is a systolic array, right? So it's a 2D processing elements, array of processing elements, and you can see the A, for example, for matrix multiplication, A array coming down, B array goes from the side, they meet, and then they can do the computation. This is actually what's going on in many of the industry accelerators, including TPUs, right? How do you design that? Then to design one systolic array is not that difficult, but how do you find the best systolic array? So this, actually, we did a careful study. We have about 7 or 8 years of research on this. So back in 2021, we published a paper called AutoSA. We can design systolic array automatically now. So there's 2 major steps that you can say 3. First, I give you a program. Can anything be implemented in systolic array? No. So you have to see whether you have a constant dependency distance, right, at every loop. And then the second question is that how do we generate that beautifully looking array? You include the computation elements, you can do computation elements. I'll be very quick that for the computation elements, so what the degree of freedoms you have? The first degree of freedom you want to decide is the space-time mapping. What set of loops goes in a space dimension? What set of loops goes in a time dimension? Space-time is always the most important decisions you want to figure out, right? The second thing is that, for example, your PE can be small or large. You can, and your array can be small or large. But no matter how large it is, it may not be able to fit the entire chip. So you have to do so-called array partition. You take the design, map it to the physical array. So which set of loops you do tiling to map. So that's actually a decision to be made. There are a few others. I will not go through details. And then you can say the magic part is that how the data flows. Some of them goes from left to right, some of them go to top to bottom. How did you figure out? This is, again, so all analytical. There's no AI involved. You do dependency analysis, find out whether you have read after read dependency or you have read after write dependency. And you can see at the bottom there. So these are the dependencies, that the vectors, and the vector tells you which direction you're going to flow. And then from there, we will know exactly how we construct the network. This is all human intelligence. There's no AI that LLM involved. And we beat, with this kind of a disciplined approach, we produce the best result. This is several years ago. The performance is not that impressive anymore, but you can see we're consistently better than published designs in getting 96, 99% of utilization. So another design is more recent. You can say, hey, syslogically is very special. Can you do more? What we can do is more general data flow. Actually, I'll yet think about the name. About that, I was debating what to put it in. I think I'm going to settle on a name called the polyhedral data flow, where each set of loop is a polyhedral code. For example, in a transformer kernel, you have a query computation, key computation, attention computation. That's a perfect example for polyhedral data flow. And so how do we get performance? If you just give it to high-level synthesis, you get 0.5 gigaflops per second, very poor performance. Where you want to do is actually to do data flow streaming. That you don't want to stream just one data at a time. You actually want to stream one tile at a time. But how big is the tile? So that's the question you figure out. These are the tiles. If you only do tile, that's not very good because you produce some computation, you write to the tile, and then the attention module is waiting, and then you write another tile, and it's waiting. So you want to overlap the computation with communication. So that's you introduce so-called ping pong buffers. So I have two sets of computation. When I'm doing ping on the buffer 1, I will generate data for buffer 2, and then vice versa. So you alternate communication with computation so they can be perfectly overlapped. And as a result, with all this optimization, eventually we can go from 0.25 to over 360 gigaops. So it's over kind of a 1000x improvement. How do we get that? Because we know we got to do we need to decide tile sizes, on-row factors, bit width, and the mapping to the SLRs and the loop permutation. This can be modeled by binary variables. You say, okay, that's a lot of a variable. But no matter what, it's like 50, 100, maybe 200 variables. Much less than millions of parameters are going to optimize, right, in a neural network or billions of variables. So this is where human intelligence make a difference. If we understand the problem, we'll come out with much more meaningful solution space. We don't need the AI to do the brute force search. And so we have an analytical formula, and you press a button. I don't want to scare you. This is a code being generated. This is not a generative AI. This is human-generated code that, with the help of the compilers. But they will achieve the same performance. You can say, hey, how do we combine all these things together, human and the machine intelligence? So this is the kind of outlook. Get to the last part of my talk. So this is, I think, a multi-agent approach makes a lot of sense. We'll have an agent to do orchestration. The program comes in, we'll do bottleneck analysis, pattern matching. We find out that, some of them are systolic rates, some of them are stencil. We all have a proven result. And then we'll have for the part it's necessary, we do code transformation, we do optimization. But once we start doing more aggressive optimization, we have to come back to do verification, test, and right. So simulation. So that's going to be a loop, and eventually I will show you that you can generate FPGAs and ASICs. So that's the whole flow. By the way, those are two real chips. I'll show you. That's designed from our lab. Then the one is a SAT accelerator on FPGA. The other one is on ASIC. Give you a sense of the complexity. Each one of them is about 7 million lines of RTL code done by high-level synthesis. So if you're talking about using LLM to generate designs, try something like this, then I will believe, right? That you have to be able to handle this complexity, not 2,000 lines of RTL or the 5,000 lines of RTL. So we don't have that built yet, but my student built a agentic system, which is very interesting, just for the kind of a program insertion problem we have. So I have 5 agents, and you keep generating solutions. The first one is to figure out if I generate these solutions, I will give it to a router agent to figure out who are the experts can generate the next move. And then the next person will say, I want to optimize performance doing parallelization pipeline. The other one says, I want to save area and try to do something. So all of this will go to an arbiter. Arbiter is going to decide, hey, this makes sense, this is probably too aggressive. And when he makes the decision, it's going to give it to a critic. Critic will see all the past designs, says, okay, this is likely to be successful, this may not be successful. So we integrated all of this together. So remember that the domain generalization problem, we use hierarchical mix of experts that when we come down to LM, DSC, this is the agent-based approach, that actually so far is giving us the best result that we have. So with that, I'm going to conclude. I think one part of the message is that carefully engineering the AI ML tools can definitely help chip designs. I showed you how do we combine GNN with LM and the capture design hierarchy, program transformations, task transfer from FPGA to ASICs, domain transfer, right, using a mix of experts. I don't have the time to include other things. For example, we can do importance-based sampling. We can learn to compare, and all of those can guide us through the design. We also have some of the work on quantum computing using some of these techniques. But I want to emphasize that AI ML is not a replacement of human intelligence. Don't write easy papers that think deeply and then trying to understand the structure of the problem we have. Maybe not the entire problem, but the sub-problems, that'll be very useful because that can be the building blocks we have. The outlook is that we want to have a multi-agent-based approach that combines machine and human intelligence. My goal is very clear, is I want to enable this young lady doing software programming to be able to do chip design. She was, when they say, chip design is just as easy as writing another PyTorch library, and we are successful. By the way, we have some success that with the course I'm teaching undergraduate CS133 in 1.5 weeks, and using high-level synthesis, and they can design the CNN accelerator in the AWS F1 cloud, right? So with that, I want to acknowledge that all the graduate students and postdocs, in particular, I want to highlight the contribution from Professor Yizhou Sun and her group, and she's a well-known expert in the machine learning community that we work very closely. It's funded by a joint NSF project and also the prison center. So I think this cross-disciplinary collaboration stimulated a lot of new ideas. I know I don't have time to go into details, but I gave a more complete talk to acknowledge what the helps I got at the Kaufman Award dinner last November. And right before the DAC, I finally got the time to upload that into my YouTube channel. I do have a YouTube channel with only 3 or 4 videos. If you are interested, check it out. Thank you so much for your attention.